Good afternoon, all. So today we're going to be discussing our very first of the hypothesis tests that we'll be doing this term. You will find them to be all pretty much the same once you get the hang of them. So today's, as I say, will be the first one that we learn, and after this you'll see that the same pattern just kind of keeps repeating itself over and over and over again. Alright, so I'm recording with my older device today, so I have to remember how to use this goofy cursor thing. So what we're going to learn today is what's called the z-test. Z-test. The z based on the standard normal, as you know. Standard normal distribution. And that is, it's normal, and we say, oops, I want to have my old tablet back, my new tablet back. Oh well. Hopefully in a couple of days I'll have it back from the shop. But remember, z is distributed, normal, with a mean of 0, standard deviation of 1. So you learned all this back in 243, and you know that we can draw a curve like this. Here's 0, and here's 1 deviation, 2 deviation, positive 3, and negative 1, and negative 2, and negative 3 deviations. Those are our z-scores. We've talked about them, of course. And so what we're going to do today is we're going to assume some things. So in a hypothesis test scenario, we always start off with some sort of assumption. Anytime you're doing hypothesis testing, you are always working under some sort of an assumption. And that assumption could be anything for the most part. But the idea here is that whenever we do it, it will always have some sort of an equals to in it. An equals to. Now, we always write this assumption as H naught. And so with the z-test, we're always assuming something about this unknown population mean. Only the good Lord knows what mu is, and quite honestly, he's the only one that cares. I am interested in knowing about where it is, so I take a sample, and I will find x bar, and then I will say maybe a confidence interval or something about mu. I honestly don't care what mu is down to the nitty-gritty, teeny, tiny 18th decimal place. I just don't care that much. But we'll always come in under the assumption that it's equal to, and then if we prove that wrong, if we prove it wrong, then we will then assume that the alternative then must be true, which will always be a not equal situation. This is what we call a two-tailed test. This will happen throughout the rest of the book whenever we're doing these tests. If you hear the idea of is, should be, I don't know, was, has changed. All those have the idea that it was equal to, it may have changed now, it used to be, it used to be, I don't know, even ought to be. Okay? The idea here is has it changed? I don't know. Is, those are all kind of keywords for equals versus not equals. That's a two-tailed test. Now this is really no different than when you did the confidence interval before. So on a confidence interval, you start off, let's say, with a 95% confidence interval. And you found these z-scores, which, as you know, are negative 1.96 and positive 1.96. Okay? And then you built a confidence interval based on that. Well, what we're going to do today in this scenario is we're going to make a z-score, all right. But this time we're going to take x bar rather, minus mu over, and it's either Sx or sigma, over the square root of n. I will say that 99.9% of the time, it's going to be Sx, that is the standard deviation of the sample. Now, I make a big deal about that because, listen, in the real world, you almost never know sigma, okay? Sigma is usually unknown. That's going to be embarrassing. It's usually unknown. So as a result, 99% of the time, you're going to be using Sx, okay? And so just don't be afraid of that. The book makes a big deal about, they make a big deal about, yes, well, you can use it if you can use a z if you know the population deviation. So that's great, but it's rare that that happens. I mean, it's rarer than hen's teeth. So you're going to use the standard deviation of the sample instead. But here's the idea. If this z you found, which is what we call a test statistic, that is just, I miss my old Surface Pro. I want it back. It's really hard to write on this thing when I can't see what I'm writing. If this test statistic is what we say in the tails, that is, in the case of 95%, from here to here, 95 in the middle, that is, if it's out here somewhere, holy cow, what's the chances that that happens? The chances of that happening are what? Slim and none. The chances of that are slim to none. This is big if H naught is true. Okay? That is a big word, if. So here's the deal. If you are out here or out here, we're going to reject H naught. We're just going to reject it. It can't be true because the chances of what we saw happening, okay, are so slim, we don't buy that. Because again, either we witnessed something very rare or my assumption was wrong. I'm more than prepared to say my assumption was wrong. I'm wrong, I don't know, 15, 20 times a day, easy. So it wouldn't surprise me if I was wrong on my assumption. Okay? And so what we'd say is this, the mu, or the mean, you could say maybe something like this, has changed, this is the big word, significantly. Now, whenever I do significantly, I just write sigly. It is a big deal. It is significant change. Now, God knows it's never going to be exactly. Like if up here on this thing you said, hey, the mean is 10 versus the mean is not 10. Well, you're never going to get x bar equals exactly 10, for God's sakes. It might be 10.2. It could be 10.7. It could be 11.9. It could be a lot of things. It could even be 9.2. That's not the point. We don't want to say it has changed a little bit or whatever. No. Significantly. That's the key word. Okay? Now, something I always do when I have this in an in-class scenario, and I think that's kind of what I want to discuss a little bit about this, is suppose you had a deck of cards. Okay? And I call somebody up and I say, all right, please take out a card from the deck. And they pull out this card. They pull out the 6 of hearts. Yay. And they stick it back in, and I shuffle 15 or 20 times. And I ask them to pull out another card. So they pull out another card, and son of a gun, if it isn't a 4 of diamonds. All right. Slap it back in. Shuffle. Have them pick out another card. This time it is the ace of diamonds. All right, put it back in, shuffle, shuffle, shuffle. Pull out another card. Oh, that's cool. 2 of hearts. Shuffle, 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 some more. Pull out another card, sir. All right, thank you. Cool. It is the 3. Does anything notice anything weird so far? Okay. Now, I love playing this to a room full of people because it's always fun in the room full of people. There's always someone who, after the first 2 cards, starts freaking out. They're all red! They're all red! To which I say, really? Because the probability that I get 2 reds in a row with replacement is 1/4. Or in other words, 25%. Well, shoot, 25%, that happens literally every day. Something like that happens. So then you shame them a little bit. And so no one says anything after the first 3 cards because that's 1/8. But people are like, I don't want to say anything. Jay's going to embarrass me. I may or may not do. After the 4th card, though, is where people should start saying something. But I've shamed them so much that they won't say anything at this point. That's 1/16, which is 0.0625. Okay? Okay? The 5th card, finally, somebody usually says, that seems weird, Jay. It seems weird. There's 5 reds in a row. To which I say, all right, well, what's the probability of that? Well, it's 1 out of 32, which is 0.03125. 3.125%. The chances of that happening is a 3% chance of that happening. If what? If, this is a big if half the cards are red. If half are red. That was my assumption, right? I was assuming that half of them were red. But what happened here? Yeah, Jay, the deck was all red. That's right. The deck is all red. Now, you can't see that because I'm telling you the deck is pointed towards me. You can't see that. But here's what I know. You can't say this. You can't say that it's all red because you can't see that. But you know what you can say? You can reject the null hypothesis. You can reject the idea that what? You can reject the idea that half, right? Half are, or I should say maybe the percentage of reds is not 50-50. Maybe I'll do it that way. What you can say is this. You can say something to the effect of, well, I don't know what the percentage is, but it ain't 50-50 anymore. Okay? The percentage of red. Good grief. My own personal pet peeve is people who write a letter, a color in a wrong color. Like those shorts that say pink and aren't pink and stuff. It drives me nuts. Of red is not 50%. Well, what is it, Jay? I don't know what it is, but I know what it's not. And that's the whole essence, you see, of hypothesis testing. A person can't prove something is this or that, but you can prove that it's not that. Okay? Like I can't prove maybe, let's say we go back and relitigate the O.J. Simpson thing. I can't prove necessarily, you can't really prove who who else didn't do it or whatever. But I can prove or I can try to show that, hey, look, maybe I can get the people to see that, hey, O.J. is not innocent, right? We could reject his claim of innocence, right? But in my mind, I can't go in there and try to, prove this or prove that. All I can show you is, hey, look, here's a pile of evidence that shows that, yeah, I don't know about his innocence, man. Okay? And really, that's all they ever do when you go to court. Anytime anybody ever goes to court, if you're being prosecuted, they're trying to prove. When they say trying to prove that you're guilty, what they're really trying to do is prove that you're not innocent. Okay? Beyond a shadow of a doubt. Okay? And that's really what it boils down to. And that's the same thing we're doing here. But what we can't know for sure We can't really ever know for sure that half of the cards are red or not, but that was our assumption. And we can't say that they're all red, but we can say that they're not half red. Okay, we can prove that for sure. Because in this case here, there was only a 3% chance of seeing what I saw. Now, one time a friend of mine did this at a convention of 7th grade math teachers, 7th and 8th grade math teachers. I swear to God, she got 7 reds in a row before anybody opened their mouth. Are you kidding me? So, if you'll do the math on that, this is 0.01625, no, 1.0505625 maybe. Yeah, whatever. It's about 1.5% chance of that happening. Okay, that's 6 reds, and then so you do that. That's about what did I say? About 7.5. 0.075. 0.07. No. 0.75% chance, roughly speaking, of getting 7 reds in a row before anybody had a fit about it. They should have had a fit way before then. Okay. Now, we can also do what are called one-tail tests. Okay, so I'll start with the upper tail. That is the idea that mu is greater than or I'm sorry, I did it the wrong way. Okay, this looked like it worked a minute ago, but now it doesn't want to work. Oh boy, oh boy, oh boy. Here we go. Let's try it again. As I said, I want to do the upper tail test. The upper tail test, mu is greater than some value, and mu is less than or equal to some value. Again, the H naught always has the equals in it. Okay, the H1, the alternative, always is not equal to, whether that's greater than or equal to or less than or equal to. Because this one is pointing this way, we call it an upper tail test. The key words here are have increased or gotten bigger, or you'll hear no more than. That's another key word for less than or equal to. These are the sort of things you will hear. Okay, and again, I could say that it's no more than, let's say, 9, or I could say it's significantly greater than 9, or it has increased from 9 because that's what it used to be, or whatever. The idea here is that we want to see, how far we are off from that thing. So when we do these, and again in 243, I know that most of the curriculum, they set up the idea of hypothesis testing, so this part shouldn't be terribly brand new, but the actual carrying out of it is going to be a little tricky for some of us because we've never actually done much of it. Here we're going to put all the alpha in this upper tail, right? That is the probability that I'm going to reject that. So again, normally we use 0.1 or 0.05 or 0.01, although this is by far the most classic method for doing it. We're going to put all that 0.05 in the upper tail. Okay? Versus the two-tail test where we split up and put half on each corner, just like that would, and again, that's just right off a confidence interval. Okay? When I make a z-score in a few minutes, and we'll do some of these here in a few minutes, in this case, minus 9 divided by sx over the square root of n from the central limit theorem. And if we end up out here, we're going to reject. Because it's 5% from here out. You see this? But if it's like out here, it's like a 2% chance of happening. Well, that's less than alpha. I'm going to reject. Now, if it's in here somewhere, I'm going to fail to reject. Because that's where it should be if H naught is true. And then the only other kind of test there is the lower tail test. And I'll go ahead and jot that down. And again, lower tail, you'll hear the idea of has, gotten smaller, has got, no, at least. It used to be 16. Can we say it's decreased over time? Things of this nature. Again, because this guy is pointing that way, it's what we call a lower tail. And the idea here is that we're going to test this guy, and again, if we end up down in here, anywhere down in here, when we make our z-score in a few minutes, if it ends up down here, we're going to reject. If it ends up in here somewhere, we're going to fail to reject. Okay? That's what's called the classical method. You found this critical area. Okay, you found it. and you marked it off. And if we're out here in the tail, well, it's from a statistical standpoint, it's a bit of a freak show. It's pretty weird if you're out here, okay? But it's only weird if what? If H naught's true. If in fact H naught wasn't true, right? Because that would mean the mean is over here, like let's say it's 16. That's a z-score of 0. But really that's what that means is mu is over here at 16 somewhere. But if in fact the whole shebang was scooted this way, if in fact the mean was more down here, why, this value you found is pretty normal. Okay, that's the idea. When you say you're rejecting H naught, that's what you're saying. In this case, in fact, that mean must be down here, which would have scooted our whole distribution of that away. And then this answer that I got for my z-score is basically right where it should be, because the mean is actually a lot closer to that. Okay? And so we're going to do several of these examples, well, actually more than several of them, so you get the hang of them as we go along. It's pretty straightforward. I'll do them in the TI-83, and I'll do them on Excel. Okay? And then I'll make separate videos for doing it with the TI-89, and I think that's all. Okay? So you need to have either Excel, TI-83, 84, or the TI-89. Okay? If you don't have one of those computers or one of those devices, then contact me and we can figure something else out. But those are the ones I'm going to shoot videos for. So here's an example here. So let's see here. Zelda, because why not? It feels that the average number of calls per day to the firehouse has changed since 2002, when it was 32. So in other words, I heard this. I heard has changed. That's what I heard. So I heard mu was 32, and I want to know if it is not 32 anymore. That is, it has changed. I heard that without anything else. So what's Zelda going to do? She's going to take a sample. She's going to take a sample of 40 days. Why 40? I don't know, because it's bigger than 30. What does 30 have to do with anything? Well, you'll recall that when we did confidence intervals, we used a z if we had an n bigger than a 30, or smaller than 30 if you had the population standard deviation, which we never really ever do. So, bigger than 40, we want a z distribution, okay? And found the sample average to be, I don't know, 34, with a standard deviation of the sample of 2.95. Okay, now they need to ask us something. So at alpha equals 0.05, has the mean changed significantly? Or another way of saying it is this, she feels like it has changed, okay? So they might say, is Zelda correct in her claim? Well, here's what I hate about the book that we have. I love the book. I've been teaching out the Blumen text for years. I really like it, with one exception. Oh my gosh, they make this giant deal out of the claim. Well, just listen. It has no impact on how I solve this problem. All right? This year I did not watch the Super Bowl. It's the first time in my whole life I never watched part of it. Not even the down. Not even a play. In fact, I didn't watch any of the NFL this year. I kind of burnt out. I just didn't watch it. Okay? Now, all those games happened whether I paid attention or not. Somebody won, somebody lost, regardless of whether I was paying attention or not. Okay? So, what's going to happen on this deal is it's going to happen regardless of whether Zelda thinks this way or Zelda thinks that way. It's neither here nor there. So we're going to go ahead and we're going to solve the problem first. Because it was 1.9, because it was 0.025, negative 1.96 and positive 1.96 are our critical values. And so we're going to go ahead and make ourselves the z-score. So it's going to be 34 minus 32 over 2.95 divided by the square root of 40. And so, they got my calculator, wherever I put it. Where did you go? There it is. I highly recommend this TI emulator program. If you don't have it for your computer, I would highly recommend you get it. It is fabulous. Okay, so apparently I lied. On this machine, the emulator is only working on the 89. So for the video, I will make an 89. I will make a follow-up addendum video to this for the TI 8384s. Okay, so it's not a big deal. They are very similar. Once you get the hang of it, you'll understand what I'm talking about. Because I think this one I can't change versions. All right, so where you're going to want to be is, okay, it comes up on the Home tab. Go to Apps. Now, you will see Flash Apps on your, or you will not Flash Apps. You will see Stats List Editor. Mine's a little different because it's a little older program. Okay, you want, so there's a couple ways to do this problem. So F6 is test, so that's second, right there. And we want a z-test. Boom. And we have stats, by George. Now, we have stats, so just hit enter, and there they are. Now, mu naught, that is what we are assuming. So you see under mu naught, it's 32. Sigma here is 2.95. Now pay attention, that's a big deal. It's very annoying how some of these, on these programs, like later on we'll do a T, and they give you the information in a different order over here. So you get in the habit of doing it one way and then they switch it up on you. So just pay attention to that. This is the alternative hypothesis. This is saying we have a two-tailed test, but we could have an upper test or a lower tailed test too. So just hit the upper, that's the two-tailed version, and then hit calculate. This is huge. Okay? So there's two ways we can do this program here. Okay? So let me just first of all bring it back out of this thing. So I'll come back to that in a jiffy. I don't know, I got a little ahead of myself. So 34, I was going to show you two methods at the same time, and then I got carried away. Let's keep going with this part first, shall we? 2.95 divided by the square root of 40. Enter. I got a z-score of 4.28. Are you freaking kidding me? Do you see where that's at? That's way out here. That's freaky. If what? If H naught is true. Therefore, what I'm going to do is reject H naught. Reject H naught. And what does that say? The mean number of calls, we have to give it their same terminology. We can't say has increased. Has changed, because that's what they asked about, significantly. Now, if you want to say something about Zelda, well, Zelda was right, yes? Or you could say reject H naught, Zelda's right, they have changed significantly. But any of those, there's a variety of ways to word this. I'm looking for reject H naught, and I'm looking for has changed significantly. Now, in the middle of this, Zelda's right, they have changed, blah, 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 blah. There's a variety of ways to state that. Okay? Now, back to the calculator, see if I can unscrew up what I screwed up here. All I did was I went to the wrong... I was just going to find the z-score first, And then I went ahead and showed you the secret button. Now, the secret button is the z-test. It's not a secret button. Anyway, you come in here and just go ahead and hit enter on this deal. And what you'll see is it tells you what the z-score is, 4.28. Do you see that? This right here, 0.000018. That's a p-value. Remember, what is a p-value? Now, that should have been talked to you about that in 243 when they first introduced hypothesis testing. But if you never got that, the easy way to remember that, a p-value is very easy. It is the probability I saw what I saw given H naught is true. Okay? There is a point, what is it, I think 4 zeros? There's a 0.00018% chance that I saw that sample that I got, if in fact the mean is actually 32. That's weird. Okay, that's highly weird, people. That's freaking nuts. Now, what I want to talk about for a second is, where does that number come from? So if you take F5 right here, and if you go in and you go to normal CDF, okay, and let's go ahead and put in negative 1E99 for our lower bound, just for fun, and negative 1.96. And of course, we want to make this a normal distribution, normal 0, 1, that is. You see, because I want this to be a standard normal. And you will see that it's 0.025. Do you see that? In other words, back up here, I don't think anyone's terribly shocked that from here down is 0.025. Well, wait a minute. I thought alpha was 0.05. That's right, it is. So when we're doing these, it's this amount plus this amount. You see that? Okay. Now keep that in mind when we go find this guy. So if you come back in here, if you go F5, normal CDF, and you put in 4.28, and then go to infinity, you will see that it is half of what we had a minute ago. You see that? It's half of it. So that's 1, 2, 3, 4, 5 zeros, and then a 9. So to get that p-value, you're going to take that value, 1, 2, 3, 4, 5, and times it by 2. That's where that p-value comes from. Okay? Now, I tell you that because I think it's important that a person knows these things. Okay? And so here's the deal. If, another way to do this testing, you can use the p-value method that literally says if p is less than alpha, you reject H naught. Okay, that's just another way of doing it. So the classical method is drawing the cutoff scores on the graph up here, like I did, cutoff scores. Put the z-score out there. Oh, Jesus, in the tails. Reject H naught. If it's in the middle, fail to reject H naught. That's the classical method. The p-value just says, here's the p-value. What are you going to do about it? Okay? Now, I'm going to show you this real quickly in Excel as well. I don't know about real quickly. I'm just going to do it on Excel. See what you think. Okay. Now, a couple ways to do it in Excel, and we'll do several of these today, so you can play along if you have it. If you go to Data, I'm looking for Data Analysis. If you don't have it, you can add it by clicking on File, and then Options, and then Add-ins, and then there at the bottom it says Go, and you want to turn that top one on, so click on it, OK, and then OK. And when you do that, over here, Data Analysis will show up. So under here, you will see a z-test. Okay, I got ahead of myself. We'll use that one later. I forgot. That was only for the two sample ones. But what I will do on this guy is this. We'll say equals norm dot s dot this right here. Okay. So if we put in 4.28, comma 1. What you will see, this is the probability that z is less than or equal to 4.28. Well, that's not what I want. I want above that. So, equals 1 minus that. That's the complement. Okay? And there's our value, 0.00009, right? So if you take that guy times 2, you will get the p-value we just found a second ago. So that's 0.000018, yada, yada, yada. Okay? Decimal places being part of it. The fact that it's e minus 5 tells me, I'm rejecting h naught. That's huge. Okay? All right, let's do another one here. I don't know. So the average, let's see, milk production. Sure. In Tillamook Creamery Association Farms has increased or so Farmer Brown believes. Okay? In other words, it's a belief. He thinks he does. By the way, most of the time when a person's doing statistics, that A, they have a dog in the fight. So Farmer Brown works for this co-op or whatever, and so maybe he's in charge of this or something or whatever. And so he has a pretty good idea that it has changed. Likewise, if you worked at the beer factory and you want to know if you're this or that or blah, blah, blah has changed in terms of sales, in terms of quality control, in terms of everything, you have some reason to believe that it may have changed, okay? And so he says it has increased. So what I just heard, I heard mean production has increased. So I heard this. I haven't heard anything else, but that's what I heard. I don't know. What does a cow produce a day? 12 gallons? I don't know. I just made that up. So what does he do? So he samples. Always. This is always the deal. So you go out and take a sample. 100 cows. Because why not? And finds X bar is 12.91. And SX is 1.7. Notice that this is awfully freaking close to this. I mean, it's teeny tiny, for God's sakes. There's hardly any difference at all. But wait. Remember, the central limit theorem says it's 12.91 minus 12. That's true. Divided by, oh, wait for it, 1.7 divided by the square root of 100. Now, this is 10. That would make this 0.17 on the bottom. So you're going to have 0.9, in essence, divided by 0.17. That's a big number, friends. That is a big number. 0.9 divided by 0.17. You get a z-score of 5.2. Holy cow! Now remember, the entrance to Freakville is right around 2 standard deviations. I mean, it always is. You're like, well, I thought some of the times we use 1.64. And that's pretty close to 2 standard deviations. 5 is nowhere near, the cutoff score. Now, I didn't tell you an alpha here, but let's just go ahead and throw an alpha out there just for a good time. Let's do 0.1. Well, if that's 0.1, how do I find this critical value? Well, I could do inverse normal on my calculator. That's one way to do it. Or I could do the same thing in Excel. So, now it's important that when you're doing this, I want to really emphasize that you want to do inverse normal, but you want to make sure that you're using the standard normal. Now, this is area to the left, so 0.9 is in fact what I want. So it's 1.28. That's my critical value. Well, Judas Priest, you're clear out here. So what are you going to do? You're going to reject H naught, and by rejecting H naught, what are you saying? That Farmer Brown was correct, right? Farmer Brown is right. This is one way to say it. Now, whether you attribute that to Farmer Brown or not, that's neither here nor there. But here's the deal. Reject H naught, that's important. Farmer Brown is right. That's nice, but not 100% necessary. Milk production has increased significantly. Sigly. Okay? Now on the calculator, if you come in here to, oops, no escape. Come in here to F6 for tests, and this is a Z-test, and we have stats. Then we're going to put in that the milk production was 12, and the standard deviation was 1 point, what did we say, 9, I think? No, 1.7? 1.7, yes. And 12.9. And 100. And this is an upper tail test, so you want to make sure you select the upper tail. And then hit enter. And you see it 5.28, that's what we got, or 5.29, I forget what it was. But the probability of that happening is 5.99 e minus 8, which is a lot less than 0.1. So I'm rejecting H naught. Okay, that's how these things will work. Now, again, same deal on Excel. It's going to be equals, you can do this all in one step because it's an upper tail. It's going to be 1 minus norm dot s dot dist 5.28 comma 1. Boom. There's my, that is my p-value. Okay. It should be exactly the same. 5.99. Oh, did I put 5? I think I put 4. I think I put 5.28. I think it was 5.29, huh? There we go. That's closer. I rounded it off. Go look at the actual z-score. They use 5.29412. So if you use all of that, this number and this number here will match exactly. Okay? It's a different way of doing it. I don't care what you use, whatever you're comfortable with. Okay? We'll do another. We'll do a lower tail. The average Algebra 1 student asks, I believe, I'm going to put in I'm going to put an I believe in here. I believe. Asks fewer questions than they used to. What in the sand hill is going on with that mess? Alright, let's try it again. Questions than they used to. Okay? That's kind of a big deal. Okay? So, you know, they used to ask, I don't know, 12 questions per month. Let's make that up. So what do? So you sample 30 kids and you get X bar is equal to 11.5. The standard deviation of 4.1. Notice that violently large standard deviation. That's ridiculous, okay? Because you got some weirdo in the crew who didn't ask any. Or maybe he asked 1, or then somebody else asked 15 or something. Then the average is still here, but it's really distributed out now. That's kind of crazy. So be aware of that. Now, by the way, if you took a sample, and the sample came out to be like 17 questions on average, then I personally wouldn't have taken a sample because there's really no way I got 17 if in fact it's somewhere around 12, okay? And I wouldn't have made the statement like I feel like they get less than. Because it has to be pretty significant before I go, I'm going to make a statement about this. Yeah, that's what I'm going to do. It feels weird. So I'm probably going to do that. So alpha equals 0.1, let's say. No, not 0.1. Let's do 0.05 again. Sure. Now remember, this is a lower tail test. Now, when it comes to testing these, whether you want to use the the classical method or the p-value, I'm fine either way. But I want you to understand both. This is a big deal to me. I think for a lot of us who are going to go into like some psychology things and places like this, the p-value shows up all the time. Okay? And it shows up everywhere else too. But I think the classical method actually makes a little more sense in some regards because it shows you kind of a picture of how far outside the quote-unquote mainstream this thing is that I saw happen. But either way works, and I really don't care. But I will ask you on the test to do it both ways. So I'm going to do 11 and a half minus 12. By the way, that gives me a negative z-score right off the bat, yes? And then it's 4.1 divided by the square root of 30. Okay? And so this comes out to be, let's get a calculator up here. So, home, 0.5 divided by 4, no, try again, stupid, 4.1, that bad, divided by the square root of 30. There you go. And let's see what that comes out to be, 0.66. We get a negative 0.6. Oh, I put in just positive 0.5. I apologize. It should have been negative 0.5. Well, where is that? Holy cow, it's right out here. You know that? That's right where it should be if what? If H naught is true. So I'm going to fail to reject H naught. And what does that mean? You could put in there that J is wrong if you want. But whatever. It's either here or there. If you put that in there to me, I don't care. J is wrong. But the Algebra 1 students, do not ask significantly fewer questions. Questions. Something to that effect. Now, of course, I can do the same bit with the stats list editor as I did before with the z-test. Okay, here we go. So, again, it's F6. Oops, second F6. There you go. There we go. Z-test. I guess I have stats. And then I'm going to plug in mu naught is 11 or is 12 under the null hypothesis. We're assuming it's 12. Our standard deviation was 4.1. And our mean was 11.5. And we sampled 30 people. And this time it is a lower tail test, which is that guy. And you will see that we get a z-score of negative 0.66. And we get a p-value of 0.25. Holy cow. Well, now a p-value of 0.25, what does that mean? It means there's a 25% chance that I saw what I saw, in essence. And this is bigger than alpha. So I'm going to fail to reject based on that. Okay, that's it. That's how that is how z-tests work. Okay? Pretty straightforward as far as the testing goes. You're going to see a lot of it. Where most people get hung up on is this book. And again, I love the Blumen book, but it gets a little annoying in that they'll say things like, "Can you reject the claim?" Oh, for God's sakes! Just do the test first. Reject or fail to reject H naught, and then go back and look and go, "Oh, is that what so and so said? Oh, then so and so is right," or "No, so and so was wrong." After the fact. So again, here is a setup. I don't even know. Let's just put one on here. H naught. I don't even know what this means. I'm just going to write it down. Oops. Then I wrote it wrong because I'm ridiculous. So H naught, mu equals, always equals on H naught. Mu equals 27, sure. The number of phone numbers you average when you go out on a Saturday night. I don't know. 27. Whatever. And blah, blah, blah. When you're all done, let's say you do this test, and you get a p-value of 0.02. Okay? Now, and your alpha was 0.05. Okay? Now, notice I skipped a bunch of stuff. All I told you was this right here. What is that telling me? It is telling me I should reject H naught. Boom. That's a fact. Comma. Now, if in the problem, Susie said, I get significantly, I do not, no, I'm sorry. Susie always says she gets 27 phone numbers. Well, good for Susie. Susie's wrong. Susie is wrong. Because if she said she gets 27, that means she was saying this. In other words, that was her claim. But don't worry about that until after the fact, you see. Go out and prove H naught is right or wrong, all right, that is rejected or fail to reject it. And then come back and go, all right, now what does that say about Susie? Well, if Susie said this is what she got, by rejecting H naught, then you're saying Susie's wrong. By the way, does she get more or less? I don't know. She doesn't get 27. She doesn't get 27. Okay. Now, another one might be blah, blah, blah. Bob gets significantly. See, Bob has significantly, I don't know. Bob eats on average significantly fewer carbs than he used to. Well, good for Bob. 100 grams. I don't know. Is it not kilograms? Grams? Milligrams? I don't care. There it is. That's what it used to be. And now he says it's less than. This is on a daily basis, okay? And he wants you to test it at 0.01. Wow. Really, Bob? That's really, really small. So we get a p-value of 0.037. Well, this is bigger than alpha. It's bigger than alpha, so what am I going to do? I'm going to fail to reject. Fail to reject H naught. Well, now Bob said he ate less than 100, so Bob is wrong. He does not eat significantly less than 100 carbs. I think it's milligrams. Is it milligrams? I don't know. You'll figure it out. That's not important. Okay? So that's the trickiest part, I think, honestly. But again, always, if you hear equals or greater than or equal to or less than or equal to, that is your null hypothesis. If you hear not equals, greater than, less than, that is always your alternative hypothesis. Sometimes, like Bob says, he eats less than. Hey, he is betting on this horse. Now remember, the horse race will get run regardless. But when this horse loses, then Bob, he lost. You could just as easily have bet on this guy. Bob thinks he eats at least 100 grams of carbs a day or whatever. In this case, then, fail to reject H naught, Bob would be right. Okay, so don't address the claim thing until the very end. That would be my suggestion to you. And by the way, I will not ask you questions specifically about the claim on the test. I will never do that to you. I will ask you to reject or fail to reject, and in your summations, you need to say something along this lines. Okay? And again, can be worded a whole bunch of different ways, but I'm looking for this piece, and I'm looking for this piece right here. Now, whether you throw Bob under the bus and say that Bob's an idiot or Bob's wrong is neither here nor there to me. Okay? But this is a big deal. I want this first part and this last part. But you can put a whole bunch of other stuff in the middle of that. Anyway, hope that, again, if you get stuck on these, for God's sake, send me an email. We'll work them out with you.